We've seen that intermediate representations are useful to decouple perception on the one side from planning and control on the other side. However, the question, of course, is how should we choose these intermediate representations precisely? And the models that we have looked at so far were using hand-engineered low-dimensional affordances, where of course also human error goes into the design of these affordances and these representations. And so the question is, can we use some more generic intermediate representations as well, such as monocular depth estimation or stereo depth estimation or semantic segmentation, standard computer vision tasks, in order to improve robustness of self-driving agents? And if we use those representations, how can we efficiently learn the perception stack? How much data, how much annotated data do we need in order to learn these models that predict these representations robustly? This is something we're going to look at in this unit. In 2019, Xu et al. Wrote an article that asked the question, does computer vision matter for action in science robotics? What they did in this article is they analyzed various intermediate representations, including semantic segmentation, depth estimation, normal prediction, optical flow estimation, or albedo prediction, with respect to their ability to lead to robust driving behavior. And they found that intermediate representations often improve results and generalization. And they found consistent gains across different simulations and tasks. And in the case of self-driving, they found that depth and semantic provide the largest gains. In particular, depth provides large gains in off-road driving, where the geometry matters a lot, and semantic segmentation is a useful cue for inner city driving, where semantic classes can be more easily discerned than off-road. And this paper here, this article, comes with a nice video with a very dramatic narration, and I want to show you that video now.
Our planet is teeming with intelligent life. Biological creatures sense the world and move through it to survive and reproduce. And soon they may be joined by artificial creatures, robots designed to see, move, and act. How should such robots be constructed? Researchers have explored two approaches. One uses structured intermediate representations to link perception and action. These intermediate representations are produced by computer vision algorithms that perform object detection, semantic segmentation, or three-dimensional layout estimation. The intermediate representations produced by such algorithms are then used as a basis for action. This approach to building intelligent systems has thrived in the fertile plains and the soaring towers of academia. Yet it is threatened by a powerful newcomer. A vigorous species is invading from the distant lands of Neurips. This species couples perception and control directly with no intermediate representations. Pixels go in, actions come out. The new species poses a threat to older inhabitants of the fertile plains. If actions can be produced directly, what is the role of computer vision? Are intermediate representations needed at all? We study this question by training agents in simulated environments. Some agents use computer vision to build intermediate representations. Others do not. In urban driving, our agents need to move through busy city streets to reach their goal. On off-road trails, the agents ride on rough mountain roads where a wrong turn can mean an untimely end by plunging off a cliff. In battle, the agents face alien monsters in a fight for life or death. We find that agents that use computer vision are hardier. They drive better, survive longer on mountain trails, and emerge victorious in battle. Even when their vision is imperfect, agents that use intermediate representations are stronger. Here we can see agents that use computer vision to drive through city streets. And here they ride on mountain trails.
Okay. So the question, of course, is what is a good visual abstraction? And in the previous work, it has already been hinted to that for city driving, semantic segmentation might be a good choice. It's maybe not a sufficient statistics of everything, but it comprises many of the aspects of the state that are informative for what we want to do. So what does a good visual abstraction characterize? Well, first of all, it has to be invariant. It has to hide irrelevant variations from the policy. And that's illustrated here on the right, in this case for an indoor scene. If we look at these two images in pixel space, they are quite different. The pixels are actually completely different from each other if we would do a pixel to pixel comparison of these two images. And therefore, it's very hard to train a policy with such inputs. On the right, we can see the corresponding representation space where a semantic segmentation has been used as intermediate representation. And we can see now that the train and the test distributions overlap in this feature space much more strongly compared to the original pixel space, as the irrelevant photometric variations in the original images have been abstracted away. And if we look just at the semantic segmentation, these two images look almost the same. Another property that we might want from a good visual abstraction, a good intermediate representation, is that it is universal. It should be applicable to a wide range of scenarios. It should basically solve all of our tasks that we might encounter in, let's say, the Kala simulator or real-world self-driving. It should be a sufficient statistics of the state. It should also be data efficient, of course. It should not require too much memory and computation in order to being produced. And it should be label efficient. It should require comparably little manual effort in order to generate the annotations that are required for training the perception stack that predicts the intermediate representation. And that's an aspect that we have been looking into in recent work. We have chosen semantic segmentation, as it has been found in this work, to encode task-relevant knowledge, for example, that the road is drivable, and prior knowledge about, for example, grouping of relevant or related pixels. And it can be processed with standard 2D convolutional policy networks, which makes it easy to deploy. However, the disadvantage of semantic segmentation is its labeling time. For example, for labeling a single image from the cityscapes dataset, which provides annotations for some of the images, the annotators required 90 minutes just to label a single image. So this becomes very quickly very expensive if you want to annotate thousands or even millions of images. And therefore it's important that we have a visual abstraction that's label efficient. And so this is what we looked into in this work called Label Efficient Visual Abstractions for Autonomous Driving, that appeared in IRIS 2020. The questions that we ask are, what is the trade-off between annotation time and driving performance? Can selecting specific semantic classes even ease policy learning? Are visual abstractions trained with few images competitive? Is fine-grained annotation, as done, for example, in the Cityscape semantic segmentation benchmark, actually important? And are visual abstractions able to reduce training variance, which is a common problem that appears when training end-to-end driving models? Here's the model that we consider. It's a standard visual abstraction model where an input image, the state or observation S, is converted using a neural network, a visual abstraction network A with parameters psi, into a visual abstraction. And that visual abstraction is then further converted using a control policy pi with parameters theta into a control command by also conditioning on the navigational command, the high-level GPS navigational command, and the input velocity, and outputs the final action. Now in this case, we considered both A and pi as neural networks. And the first neural network is the visual abstraction network that maps the input state or observation, the image S, to the representation R. And the second is the control policy that takes R, C, and the velocity and maps that to the action A. And of course, if we combine both, if we compute pi of A of the input observation or state S, we obtain the action A by composing these two functions. In order to train these two models, we need labeled data. And we need, in particular, NR images annotated with semantic labels, and we call that set R, in order to train the representation, the visual abstraction network A. And this data set is composed of input images and semantic ground truth label maps R. We further need NA images annotated with expert actions to create the action data set A, that is, the action data set A that comprises the pairs of the input image and the corresponding control command as measured by the sensors that measure the steering wheel angle or the acceleration commands that are provided by the driver. Now, of course, it's much cheaper to get the labels for the action data set compared to the labels for the semantic data set. So we assume that there is much more data points available for the action data set compared to the representation data set. Training then works as follows. We train the visual abstraction network A using the semantic data set R, the small semantically annotated data set R. And then we apply this network to obtain the control data set. We can apply this network to all the inputs that we have seen while driving around. And we combine this with all the measurements that have been taken by the vehicle. These are the ground truth control signals, the steering wheel angle, and the acceleration A. So through this conversion, we generate this big data set now with maybe 100,000 or millions of data points in order to train the control policy using that large control data set. So we have a small data set to train the abstraction network and a large data set to train the policy. The model that we use is the conditional imitation learning model SILRS, the state of the art of 2019, which uses as input the visual abstraction R in this case, not the image, but now we input R into this policy. The navigational command as also in the original model, and the vehicle velocity as input. So a single image together with the vehicle velocity is a pretty good sufficient statistics of the state actually. So you don't need to have all the previous frames. Turns out that if you have just one frame and the velocity, you can do a lot of the things that you want to do in inner city driving. And the output is then the action or control A, and also the velocity, which is used also by SILRS as a regularizer to avoid some of the causal confusion problems that occur. And then we optimize a standard immutation learning loss where we minimize the discrepancy between the predicted action and the ground truth action and the predicted velocity and the true velocity. This is now demonstrating the visual abstractions that we use. The first thing that we consider is privileged segmentation, which is the ground truth segmentation. We work with a simulator, so we can also provide the ground truth segmentation as input to the model in order to verify that this is actually not like it's kind of an upper bound for our analysis. Like the model, like the policy can never perform better, or it shouldn't perform better with a predicted semantic segmentation that is faulty compared to the ground truth semantic segmentation. So we have this as an upper bound. But it turns out that we can come pretty close to that upper bound actually. And that other aspects, such as the number of labels and the chosen classes and the way we represent the labels, are more important. So in this case, we use 14 different semantic classes that you can see here with different colors, for example, lane markings or the road or pedestrians and cars and traffic lights and buildings and so forth. We also consider a reduced set of semantic labels. In this case, only 6 classes are shown that we deem to be relevant for self-driving, and also in experiments have turned out to be most relevant for self-driving. So the 6 classes that we have here are the roads and the lane markings and the other vehicles, pedestrians and traffic lights. Of course, in practice, we don't have access to, like when we run our agent, we don't have access to the ground truth semantic segmentation. So we need to live with inferred segmentation that's inferred by our perception, by our visual abstraction module. And what you can see here is semantic segmentation results for the same image as before. Now the semantic segmentation model has been trained with 14 classes, and it's a state-of-the-art semantic segmentation model at the time, which uses a residual network and a feature pyramid network with a segmentation hat. We do the same analysis also for a reduced set of semantic classes. In this case, the segmentation model was trained only on 6 classes, 2 stuff classes, and 4 object classes. And again, we use the same network. We can see the results differ from the results before. And then we also design a hybrid that uses 2 stuff classes. It uses a segmentation model for the 2 stuff classes, road and lane marking, but an object detector that only predicts the bounding boxes, not any more pixel precise instance segmentations, but predicts or semantic segmentations, but only predicts the bounding boxes of the 4 object classes, vehicle, pedestrian, and red or green traffic lights. And this is illustrated here. This is an output of the actual semantic segmentation and object detection model overlaid. The advantage, of course, when reducing the number of semantic classes and simplifying the representation is that also the annotations become easier. The annotation time reduces. And at the same time, the hope is that the model can focus on what's actually relevant. It doesn't waste any capacity on the irrelevant aspects of the scene and puts all of its energy into predicting what's actually relevant for driving. We evaluated on the Kala 004 no crash benchmark with random start and end locations, and as metric we use again the percentage of successfully completed episodes, or in short the success rate. And we consider different levels of difficulty: empty scenarios, scenarios with regular traffic density, and quite dense traffic scenarios. In order to identify the most relevant classes, we updated from the original set of 14 classes different classes step by step. And the results that I'm going to show you now are for 14 classes, which comprise road, lane marking, vehicle, pedestrian, green light, red light, sidewalk, building, fence, pole, vegetation, wall, traffic sign, and other, to 7 classes where building, fence, pole, vegetation, wall, traffic sign, and other have been removed as they have been deemed to be less relevant for the driving task. And then we have a case where we only consider 6 classes where also the sidewalk class has been removed. And we have another case with 5 classes where now also the lane markings have been removed. So here are the results. We can see different plots for the different levels of difficulty: empty, regular, and dense. And the right plot here is for the overall performance across all the levels of difficulties. On the bottom, you can see, like on the x-axis, you can see the number of classes that are considered, and on the y-axis, the success rate that has been obtained. And the success rate is further divided into successful episodes, which are the green plot. The higher the better. And then unsuccessful scenarios which happened either due to timeout because the vehicle stopped and didn't reach the goal in time, or because the vehicle was colliding, here in red. So the best would be if the entire plot here would be green. And what we can see is that when we move from 14 to 6 classes, we do not hurt performance significantly. On the contrary, in some cases, we even improve the performance. This can be shown here. This can be seen here in the empty scenarios and also in the dense scenarios and the regular scenarios. However, we see a drastic performance drop when the lane markings are removed, which indicates that the lane markings are actually relevant to driving, so we shouldn't remove them from the representation. Here's a video that compares the different cases for the privileged. This is results for the privileged situation where the ground truth semantic segmentation has been used. And you can see here how the performance drops from a success rate of 78 to 28 when removing the lane markings. But these two models perform similar, or actually the model with less semantic classes performs better than the model with more semantic classes because it doesn't distract the policy as much. What we can see here now is a comparison of 6 versus 14 classes, where we compare also the results with the inferred semantic segmentations in red to the privileged ground truth semantic segmentations in green. And what we can see again is that there is a performance drop when using the inferred segmentations, but it's relatively small. So we go from, let's say, 67 to 59% success rate. But of course, in practice, we don't have the ground truth segmentations available, so we have to live with the inferred segmentations. What we can also see is that the 6-class representation consistently improves upon the 14-class representation. In all of these plots, the results that are obtained with the 6-class representations are actually better than the results when using 14 classes. And therefore, for the next experiments that I'm going to show you, we always consider the 6-class representation. Here's a comparison of the effect of using a hybrid representation that's comprised of bounding boxes and semantic segmentation only for the stuff categories like road and limb markings. And we can see that the performance of the hybrid representation matches the standard segmentation performance, and in the case of difficult scenarios even slightly improves. However, the annotation time of the standard version is significantly higher because much more of the objects have to be delineated pixel accurately, have to be annotated pixel accurately, while with bounding boxes, drawing a bounding box is much easier and therefore takes less time. So we can reduce the annotation time without hurting the overall performance from 300 seconds to 20 seconds in this case. In summary, this is a summary slide from that paper that illustrates all of the results on one slide, basically. If we train a direct perception model, a visual abstraction model with 6,400 finely annotated images and 14 classes, the annotation time is 7,500 hours and the policy success rate is 50%. In comparison, if we train with only 1,600 coarsely annotated images, this is the hybrid representation, using only 6 semantic classes. So we have a coarser representation, we have less semantic classes, and we have less annotated images. Then the policy success rate is 58%, but the annotation time reduces to only 50 hours. What this means is that it's important how to choose the visual representation, the visual abstraction layer. And annotating more images is not always needed if the classes are chosen wisely and the representation is chosen wisely.